How do you want to do with questions?
So local questions, maybe they could just blurt them out. Maybe I guess, maybe paraphrase it before you answer it. Let's
Yes.
say that happens.
Yes.
Uh,
Got to remember that.
But, my guess is there will be no questions during the talk.
Okay.
And we'll keep them to the end and but there might be some in the chat room.
Okay.
So if there are some in the chat room, I'll be here and I'll just raise my hand and ask a
Okay.
question.
Yeah, I think it'll be good. I feel like once you get questions in the middle, it gets people more engaged with the idea that they can.
And you want that, or
I think it's
you're
good. I think it's better.
Yeah,
I
okay.
feel it's kind of better to, because I don't know, once you feel people are engaging, then you can also easier to gauge your rhythm.
Yeah, okay. So I'll encourage people here to. How many do you? By the way, are you free afterwards, or would you want to check out the panorama room, see if it's still happening?
Yeah.
Because it should be. We're good to go. All right, it's a pretty full house today. Welcome everybody. We're having the last CFEM and UBS AI and Data Research Seminar. I'm really excited to have Achintya Gopal talk about NeuralBeta and the importance of network design. So I guess it's a little bit of a mix between betas, an old-fashioned finance concept, and some new fun machine learning stuff that I'm sure you'll tell us very soon more about. Another thing about Achintya is he's been sponsoring a very fun project on election arbitrage. I know some of you in this class have been working hard on it, and so basically, and also you were a speaker last year, so thanks for really participating in CFEM the last couple of years. So he's a great speaker, and he likes to be interrupted. So if you have a question off the top of your head during the talk, please feel free to say it. Also, if you're joining us online, feel free to add questions in the chat room. What else? Follow us on YouTube. What else? Well, without further ado, Achintya, good to have you.
Thanks. Yeah, so like I said, my name is Achintya. I'm a machine learning quant researcher over at Bloomberg. Basically, I'm in this quant research team in the office of the CTO. And so a lot of what I've been working on in the last few years has been basically at the intersection of machine learning and finance, right? I think that there's a lot of cool stuff that can be done with machine learning. And I think especially understanding kind of like how neural nets work and everything kind of allows you to have almost, I would call it, more fun with what you can do with them in finance. And so I thought that'd be kind of a cool theme to go for today. So I'm going to try talking mostly like as at least for a problem, NeuralBeta, but I'll then towards the second half, I'll start talking about how using domain expertise, using prior knowledge, good design principles, what you can do to kind of improve performance of your model by, again, just having fun with your neural nets. Right, so quick outline, intro, what's beta? It is a pretty old concept at this point, so won't be spending too much time on that. But from there, we'll kind of transition on to basically what is NeuralBeta, basically kind of like a basic architecture of it, quick aside on the concept of weighted loss functions and then evaluation, and then the part that at least in my mind, that's a little bit more important in my mind is the importance of network design. Network here meaning like the neural networks, basically how you're going to design those. And then finally we'll conclude. Cool, so beta, right? So kind of it was introduced within this CAPM model. Intuitively, the idea is to think of returns of a stock as having a component that's correlated with the market, some risk-free rate, and then just some idiosyncratic term. That was kind of the original version. From there, people pushed it to be, okay, what if there's not just a correlation to the market, but what they call other factors? So then you can make it like basically kind of like a multi-factor model. So you could have a market factor, a value factor, growth, industries, whatever. The idea basically being that trying to decompose returns into these components. And one thing you could then do is that if you had these betas is that you could hedge away these risks, right? I don't want to be exposed to the market. I don't want to be exposed to certain factors, but I do want to make a directional bet on another factor. So how would you do this type of factor modeling? You kind of have three approaches. There's the Barra style, which is where you know the betas, but you have to infer the factor returns. The Farmer-French approach, where you know the factor returns, you don't know the betas. The statistical approach, where you don't know either, and you try to infer it. And I'm not going to present it today, but it was something presented just this weekend, so shameless plug. There's a paper I wrote on neural factors, which basically how to use neural nets for this same problem of a statistical approach to learning factors. But back to the actual problem. For beta, the way we can think about it is I kind of hinted at it earlier, what's a use case of beta is that you can use it to basically hedge out certain risks. And keeping this in mind, this will kind of come up a lot more in the next slide. But so now that's kind of like a little bit of a quick little history lesson, let's call it. Let's actually talk about what is it we're trying to do. So thinking about beta. Basically, what is beta trying to do? Beta is basically just trying to explain y as some linear function of x, right? Classically, beta usually refers to stock returns and market returns, but at least when I'm talking about beta in this presentation, I'm kind of meaning it in a more generic sense of this linear function, right? Y could be a change in option prices, and x could be a change in the underlying asset price, right? So in the options world, that'd be called delta, but just as a catch-all, I'm just calling all these linear type concepts beta. So given that this is what we want to do, the first thing we have to do is basically define an evaluation metric, right? How are we going to know we have a good beta, right? You can't really do machine learning without actually having a way to evaluate if you're doing a good thing. And so in very, very classical machine learning, usually what you would do is you would have observed the target, and then you have some loss function with that. But in this scenario, beta isn't observed, right? So I can't do a simple like mean squared error against the prediction and the observed beta. So what can you do instead? Well, we can keep in mind the use case I kind of hinted at of using it for hedging. So what if that becomes basically our loss function? So we can put it this way. So what does this mean? So this little beta e function thing, like in words, you can basically think of it as the estimate of beta using data up until today. And now this loss function basically is lingering variance, right? If I hedged y with x using beta, right? So kind of in words, basically what is it we're trying to do? We're basically claiming that a good beta today is a beta that will reduce variance tomorrow, right? And I think, and it's kind of important to always note that, obviously when we're doing machine learning and things like that, to a certain extent, it is about trying to figure out how your problem is some out of sample type task, right? So that's all this is. So now that we have an evaluation metric, it also means we can optimize it, or take differentiability. So if you kind of think of it this way, we have data, which goes into a blue box for beta, and then we have a loss function. We can then test out different methods. We could do just a regular linear regression. We could do a weighted linear regression, Kalman filters, whatever, a ton of other methods. One thing that's mentioned in the paper, but we're not going to really consider it here, is that you could always add an alpha term into the objective function. We're just going to assume that's 0 for now, and then maybe let's say future work to see what happens if you actually try to model that as well. All right, so as I said, the most classical approach, of course, is just the regular linear regression. The equation I put is the univariate version of beta, just I feel it's easier to look at than with all the matrix multiplications. But the general gist of this is that this is basically derived using an assumption that the beta is constant in your look-back period. I think one thing that's probably worth noting here is I've had a lot of conversations about this, so I think it's probably worth just in case someone else is thinking this. Often when this equation of beta is derived from an optimization function, but that doesn't necessarily mean that that thing you optimized was your actual, what I would call your actual objective. I often call that basically like a proxy objective. So assuming beta is constant, then presumably a good proxy objective function would be using beta to hedge the past. But the thing that really matters after that is seeing how well will it work tomorrow. And so, yeah. And so one thing you could obviously do is try to optimize the look back window. And if beta were actually constant, the optimal look back window would be as long back as you could go. But as we know, beta is not constant, right? And so what people then try to do is try to add some type of weighting scheme, right? So you can just use like an exponentially weighted regression. Basically add more weights to the recent data points. Basically, you're claiming them to be more important. I wouldn't, so yeah, and so from this case, then we can start to optimize alpha, right? Basically the half-life or the weights. I think the important point here now is that sometimes it's kind of viewed that beta is like a parameter that you're optimizing, and then alpha would be like a hyperparameter. At least within this framework, it's not that, right? Beta, like the function, basically beta here is like a function where it has to take the data and output something. And then things like alpha is the parameter that you're optimizing. But of course, a natural question is, why exponential? Why do we have to do it that way? Why not something like, I don't know, a power law? Why not things with like multiple bumps in there? Like, why be bottlenecked in this specific functional form? Can we go more flexible? And so what if we just replace it all with a neural net, right? So instead of having a specific derived function that takes a time series and outputs beta, what if you just take that time series, put it into your neural net, and then get beta, right? And again, because that function is differentiable, the loss function is differentiable, we can optimize the whole thing and see what happens. So what neural net should we use here? So when I think of like basically architectures, right, I think, or if anybody's thinking about them, I think the best way to kind of think about it is basically just ask yourself these kind of 4 questions. What is the inputs? What are the outputs? What are standard tricks to improve the model optimization? Basically, are you ensuring you're using what I would call like the best design principles you can in the design of the neural net? And then can I modify the architecture given domain expertise? Right, so in our case, the input is a time series of X and Y, right? Kind of similar to what the input to OLS is. The output will be beta, which is going to be a vector of length X. I try to just say it in a more generic sense that if you're doing univariate, like against the market, it would be one output, but you could also formulate the whole thing in a multivariate setting. For standard tricks, there would be stuff like residual connections, normalization layers, et cetera. I'll go into those a little bit more as well. And of course, the domain expertise one, I'll go even more in the next section. So just thinking about the fact of like what the inputs are and the outputs are, the first obvious thing to use would be some type of like recurrent neural net, right? So an example of a recurrent neural net is basically like a GRU or a GRU. There's many others, there's LSTMs, and this kind of, I would call a revival of recurrent neural nets over the last year or two, where now we have like S4, Mamba, Min LSTM, XLSTM, people having a lot more fun all of a sudden again on designing recurrent neural nets to see if they work. Just because I'm going to be focusing more on, I'm not going to talk too much on this one. I'm going to focus more on the transformer architecture, mostly because this is what kind of gave us the best performance later down the slides. So let's just talk about this one. So I think at least semantics wise, I think it's probably good to at least differentiate what does attention mean versus transformers. So basically, attention, you can think of it as like just a type of layer, right? The same way a convolutional layer is a layer. A matrix multiplication is a layer. It's basically just a type of function, but that doesn't necessarily mean that just using that function and then stacking them is the best way to do it. You can think of a transformer block as basically saying, okay, attention is a cool function. It has the properties I want, but how do I use this in conjunction with other layers and other design things I can do to create an architecture that will actually optimize well, right? So, and that's kind of what this is trying to show. So in essence, starting from the bottom, what would you do? You have your time series, X and Y, and then you would embed that basically with some type of linear layer along with time. Then you would pass that into an attention layer. And so, and then there'd be this kind of like residual connection, right? Basically, after this attention function, basically kind of mixes your inputs, you add it back to the original input. And then you repeat it with, then you do this again with an MLP layer. And I try to show this with like colors, like they're all the same color because you use the same MLP for every time step. And then again, another residual connection. And one could argue that like, to a certain extent, these blocks have a certain level of almost, let's call it magic to where they came from. But in essence, a lot of these, let's say, things that people tend to use in architectures just come from the fact that people have run a ton of experiments trying different general structures, and eventually we hit structures that work well. And then there tends to be some theoretical justification after the fact, and there are some, on why this type of setup allows for better optimization than if you didn't have, like, say, these residual connections. So for attention, I'm not going to go into too many details, but as Sasha mentioned, I did do a presentation last year about supply chain. And so there, I do go into more details in that one about the specific function of attention. So if you really want to know the exact, like, nitty gritties of what's going on in there, you can check that out. But not going into the nitty gritties, at least at a high level, the way to think of attention is that it's a layer that can take a set as an input, right? And then the number of outputs are the same as the number of inputs. And importantly, I said a set. So basically, it doesn't actually care about the ordering of the inputs. And in some problems, that's actually a good thing, right? Sometimes I'm just trying to model a set of objects, and it would be nice to not have to be forced to impose a structure. Obviously, if I'm doing time series, there is an ordering. And so that's why there's this time part as part of the inputs, right? It's important so that the model knows this is the first time step, this is the second, this is the third, et cetera.
Can you comment a bit on the coding, or like, does this involve a package? Would this entire architecture be 5 lines of code, or would it be
That's a fair
much
question.
more complicated?
So this one, because, so I think it's kind of funny. So the language I tend to use, the library I tend to use is PyTorch. And PyTorch tends to give you mostly just like individual layers. So like almost like usually like just attention, and then you'd compose it together in the right way. But funnily enough, they've given transformers directly in the package. So at least if you're using transformers, you don't have to, like, I don't know how many lines, but very few lines. Basically, this part you can do with very few lines. There's a lot of hyperparameters that you would have to that you can play with, but it's just one object with a few like with different init arguments. Handling the time component isn't built in. How you want to handle it, there's a lot of good tutorials, but again, you can do that in a few lines. And then, yeah, so doing this type of architecture is actually not too hard. Later on, I'm going to be talking about like just that NLP component, which actually by itself is quite useful, even if you're not doing time series. In that case, that's not built into the library, so you'll have to implement it yourself. But even then, that's like, I don't know, 20 lines max. And that's if you want as much flexibility in that one block as you can put in there. So yeah, PyTorch. Yeah, so that's the idea here. That's one general form of an architecture. There's obviously a linear layer at the end, mostly because I guess one thing I didn't mention anywhere in the slides, but usually good practice is for the first linear projection to project up, or I guess basically lift it. So if your input dimension is 3, go up to like 16, 32, or 64. My default has become 64 or 128 as like the first set of hyperparameters I set, and then afterwards I'll tune them later. Okay, so that's the architecture for NeuralBeta. And so a quick aside on the loss function. One thing I've kind of noticed people talk about a lot as well is trying to insert weights into their MSC. And it's kind of interesting. I feel like there's always the question of what weights to use. I've seen people use market cap. Some people say use square root of market cap. And I don't know, they kind of adding more hyperparameters such as that always makes me feel like there has to be a better approach. And so, so basically the question is, instead, can we maybe optimize the weights instead of having to predefine them? And so there's kind of 2 ways to do that. I'm going to focus on one interpretation, which is, instead of thinking of this as mean squared error, you could think of this as maximum likelihood estimation instead, right? In that case, you could imagine using a normal distribution. And if you were to do that, expand all the terms, you get this, which is basically just a weighted mean squared error with some extra term. And so at least looking at it this way, I think rephrases the weights as, don't try to weigh by what you consider as important, but more by basically by the noise of the data, right? How much variance is there in Y after accounting for X? And the thing is, once you have this view of it, you can also just change your neural net, have 2 outputs, and then just directly optimize that loss function. right? And so now instead of having to even assume the amount of noise you have in your data, you can just directly learn it from the data itself. So it's kind of almost as just an aside, but I think even with this case, and even maybe even with the weighted linear regression, there's kind of always this theme, at least in my mind, that if you see somewhere where there's a whole like tuning and playing around with weights, chances are there's probably a way to take a more direct approach where you just optimize them instead of having to play with them as like a tuning parameter. Just to give a little bit of intuition on that loss function, you can kind of think of it as the first term. Imagine I try to optimize sigma just in that first term. What would happen? The optimal sigma there would be infinity, right? The bigger sigma is, the smaller that term gets, and so it would just vanish and there'd be no value. The second term is the opposite. The optimal value for the second term is 0. So at least from an intuitive perspective, you can almost think of these two terms as fighting each other, where the second term wants to make sigma as small as possible, but the first one wants to make it bigger, so that way it's easier to describe the data. And obviously, there's a whole obviously, it's just the log likelihood, but at least for an intuition, you can kind of think of it that way. Okay, so now that we have a model and some discussion on the loss function, let's do some experiments. So the first set of experiments we did is with simulated data. There's real data later, but why do we like to do some simulated data experiments? One, there's actually a ground truth beta that we can compare against. We can kind of build some intuitions maybe on when it does well, when it doesn't do well, and how do different approaches compare. And then the one question that we had is that, I think someone is that, does optimizing our loss function actually optimize the mean squared error between your estimate and beta, right? And so there'll be a later slide showing whether or not how like correlated these two approaches are. And obviously but obviously you can't really use that loss function in real life. It only works on simulated data. So it's basically just hoping that at least on simulated data, if it does work, that gives us at least some hope that it will work in real life. So we have 3 simulated data sets. First one is just a constant beta. So we just create a time series of length of 65, because 64 look back, 1 look forward, 1 forward. The X's are sampled from the student T, just because adding heavy tailed is kind of nice to make it somewhat more realistic. Beta sample from a normal centered at 1, and then there's some noise added where the variance is also different per time series. And then we generate 200,000 of these time series, and then we split that into train, validation, test. One difference between this type of data and real data is that it's not like we created one really, really long time series. We created basically a ton of small 65, a length of 65 time series. The goal wasn't to make the most realistic experiment data, but at least to get a set of at least data that we can see what happens and build some intuition. We also created 2 other data sets. I'm not going to go into the exact details of the generation. It's in the paper. But basically, we did one where beta is a step function. So basically, the step where it does the step is randomized, and the values it goes from and to is randomized. And in each time series we generate. And then we do one with sine waves, basically with a random like amplitude and random wavelength. Basically, that's going to be useful for our experiment to see how well these methods are at being adaptive. So just some kind of results on some examples. The top one is just one very specific like instantiation of a row and just seeing what happens on the predictions. So this one we kind of made a little bit longer of a time series just so that we can see how it predicts over time. In the case of in the case of the flat one, it's kind of wobbling all over the right answer. But again, there's obviously noise given the fact that it's only a look back window of 64. In the second one, you can see that obviously OLS it doesn't respond fast enough. This is the EMA neural net does. And third one with the sinusoidal, same pattern is observed. In the table, and what we compare against, basically what we look at is the percentage improvement of the RMSE against OLS. That's why OLS always has 0 in all our tables, is because obviously relative to 0, relative to OLS, there's no improvement. And then everything's a percentage from there. In the case of constant, all the other approaches do worse than OLS, which makes sense. It's a flat beta. OLS is basically the optimal solution. You can't really beat it. In the other cases, of course, though, the other approaches are better able to handle those data sets. Looking into some subsets of different parts of this synthetic data, simulated data, with for the sinusoidal one with different wavelengths. Basically, on the rightmost, we have what happens when beta is basically a little bit slower moving. How does it perform? It still is outperforming OLS, but it has some level of noisiness. But again, it's able to kind of handle it. Then if you go into like the middle, where the periodicity is a little bit like basically it's like moving a little bit faster, it does seem to be able to handle that one. And then again, with like really, really volatile, it's again better. It's a little bit more responsive than the baselines, and more importantly, it's not too noisy.
It's like the weighted least squares doesn't do that bad.
So I think it's the different subsets of the data. Basically, if you look at different subsets of the data, that's where you can see more patterns pop out. And that's kind of the idea here, is that like when you're doing ML stuff in real life, they're like, while average statistics are useful to look at, it is also useful to like break it down to different situations. And that's kind of what it's here, that we can kind of like pinpoint specific situations where a neural net is doing better than another approach.
But I mean, in the weighted least squares, you play around with the exponential weights, or did you just pick one?
So in this case, we only picked, we tuned one for the whole data set, which obviously in the case of what in this data set, we would obviously know that we'd want something different for each one. But it's kind of a chicken and egg problem with the way the data is created, because each row is only of length 64. So you have to kind of like at least cut out the windows. And are there ways to improve it? For sure. But to a certain extent, at least the main test here show that at least a neural net is able to be adaptive. But yes, I do agree that with a lot of these approaches, including this one, there are tricks to help improve the performance baselines, which again is important to do, right? I think, but you'll kind of see in later ones where like how to get also the neural net to do better and stuff like that, using the intuitions of these types of things that we're mentioning. And then, okay, yeah. And so then just comparing the whole like optimizing the RMSE of Y versus RMSE of beta, we could see across different hyperparameters that they're quite correlated. You know, basically if we pick the model that has quite low RMSE of Y, we're also picking a model that has a low RMSE of beta, which is good. That's kind of what we would want to see. This is across hyperparameters. And then we did another experiment where we can just watch, we could see how it looks through the epochs of training. Right, so what green is like the beginning of training, bluish is towards the end, right? And so you can kind of see that, you know, RMSE Y is like obviously like traveling down that line, and then as it's traveling down that line, it's also going down on RMSE of beta until it reaches kind of this like little corner, and then at the corner it just starts bouncing around. You can kind of think that bouncing around as basically once it's learned the general patterns, it might be slightly overfitting, so it might learn the RMSE Y a little bit better, which will then give a slightly worse RMSE beta, and just kind of jumping around in there. Finally, we did a market data experiment. The universe we used was the individual stocks of the S&P 500. And we did two experiments, a univariate and multivariate. The univariate is where we just use the market factor as the X, and then a multivariate where we use market size and value as our X. And then we have a training period, validation period, and test period. And obviously, and I guess maybe I didn't say it, but I hope that it can be taken for granted that obviously all the results are out of sample. I would almost say I'm generally of the opinion that there's no real value of in sample unless you're trying to figure out if your model's underfitting. Otherwise, there's no need to talk about it. So in this case, and I think this is important because this is where the second half of the talk will eventually go, is that in the case of the univariate, the neural net is able to outperform both OLS and weighted least square, but in the multivariate case, it's much worse than OLS, right? And so this is going to be kind of like what sets up the theme for the next half. But the main thing I kind of also want to point here that I think is important, like for anybody who's also just doing machine learning, whether it be research or something, I think it's usually always good to kind of have two baselines, basically because a metric by itself rarely means anything, right? It's only useful in the context of another approach. And the value of having two baselines is that, at least in the case of this, the way I think of it is that OLS is like the simplest thing someone would do. And then when people are trying to make their model a little bit more complicated, they're willing to do the weighted linear regression because they believe that you're going to get a performance boost. So knowing that that's the amount of performance boost you get by doing that, it gives you at least some context of how much the neural net is really giving you. Because I remember when I didn't have that column and showing 0.3%, it really seems like very little. But then when you see that even a weighted least squares only improves by 0.12%, then all of a sudden the neural net seems like it's actually quite a bit better. It's finding a lot more patterns than just doing the weighted linear regression. Okay, so that's the first half, basically where we talk about NeuralBeta and this general setup. Now, the part that I was kind of looking forward to, the importance of network design. So when thinking of a neural net, you can basically think that there's three components of it that actually make it work: the architecture, the initialization, the optimization, right? It's all three of these that kind of interact with each other, and that making a good model means you have to have all three being really good. So in terms of optimization, what do I mean by that? Basically, just like you have to, we're training these with gradient descent. That means that there's been a lot of literature on how do we make sure that gradient descent is able to optimize this well, right? What do the local minimas look like? Do some parameters learn better than other parameters? Stuff like that. And so, and basically the way you're going to think about, one way you can think about this is that it doesn't matter if a model is a universal approximator to a certain extent. You can have two models that are universal approximators, but if gradient descent doesn't enjoy optimizing one model but is better at the other, like the second one is going to be the one that to use. And then, of course, the other part that I mentioned that's important is the architecture. The way to think of the architecture is that it's basically functional priors, right? It's biasing your model to learn specific types of solutions. So if you think of, like, say, images, comparing convolutions versus standard neural nets of just like linear, nonlinear type layers, like the MLPs. Why is it that convolutions do better? It's not that they have less capacity, right? On many data sets, people have shown that even the convolutional nets can memorize random labels, right? So it's not that, oh, it's that we finally restricted it in such a way and that's why. What's happening is that it's biased to a better solution than the MLP is. Right, and so that's kind of where architectural design, a big part of architectural design goes into, right? How can you add finance priors into your functions? And I would argue that the fact that the neural nets that we have today from the ML community are basically what functional priors work well on their data sets, right? They may be a broad set of data sets, but nonetheless tuned, let's say, to that family of problems. So, speaking of at least the optimization, let's give an example. So the standard architecture people will tend to do for, let's say, tabular data or something like that is usually of this form. It will be just linear, nonlinear, linear, nonlinear, linear. And so, yeah, nothing more to say about it. That's kind of what it is. However, two consistent themes of neural network design is A, normalization layers, which people do use in this. They'll add batch norm or layer norm. But the second most important one is residual connections. That seems to be...
In the sigma?
Oh, sorry. Sigma here is supposed to be just like a catch-all for like a nonlinear activation. So like think of ReLU, GALU, CLU, Wish, but there's too many. But basically, it's just like an element-wise nonlinear activation function, nonlinear function. So just to make sure everyone knows, like ReLU is just describe it. I don't want to say the equation, which is max 0x, because that's not imaginable. But basically, if it's negative, it makes it 0. Otherwise, it's linear, right? It's just a way to add a nonlinearity into the model, and then you can show that as long as your activation function is not a polynomial function, it will be a universal approximator. Yeah. Help? Cool. So yeah, so then the two design principles, normalizations and residuals. Even not in this context, right? I'll go into my rant later. Residual connections. So basically, instead of doing like basically like linear, nonlinear, linear, nonlinear, what you basically will end up doing is linear, which again, it should project up to a higher dimensional space, and then you'll kind of go like on a tangent where you'll do layer norm, linear, nonlinear, linear, and then you add it back, and then you just stack these, and then eventually one more linear layer at the end to project to the size that you care about. So I'm going to quickly give a definition of layer norm here. This ln layer norm, what is it? All it is basically you take the vector, like the embedding, quote unquote, of your input, you compute the mean and standard deviation of that vector, and you normalize by that. Why? Basically, people have found that these types of layers, again, help with the gradient flow. It makes sure that basically the gradients are able to propagate all the way back to the earlier layers in the model. The other thing is the residual connection, which is also really important for gradient flow, right? You can kind of like intuitively think of it that basically if there's a gradient coming from y and it has to get to like say W2, it doesn't have to just keep colliding through all those nonlinear activations. It has like these linear shortcuts to get to, for those gradients to get to those parameters. And so hopefully that gives a really small intuition on like why this type of architecture would have a better gradient flow. And the other thing I think that's also a reason this thing is actually quite useful, at least in finance, is that it is so much easier to learn a linear function, this model, right? In this case, all the model would have to learn is to set W3 and W5 to 0, and you got a linear function. In the previous architecture, learning a linear function is actually really hard, right? You have to kind of almost align all the nonlinearities in like this perfect way, so that way it will be a linear function at the end. And so kind of having that in mind, that the features you'll create, having a good, strong linear connection between those features and your target is actually a good thing because this model can utilize that to its benefits. So actually applying this, like some results, one example we tested this out was like say like fast pricing of like Hessian European options. Exact problem doesn't matter. It's just a data set where you have about 7 inputs, you have 1 output, basically noiseless outputs, and then you're just training a neural net on it. And in this case, so the y-axis is the mean absolute error. X was just different amounts of data points. We were just looking at how that scales. But the main thing we kind of found is that if you go from non-residual to residual, it cuts the error by nearly half. Another example was imputing vol surfaces with VAEs, which is on archive now, like I think since last week. So if anyone wants to check it out later, you can. But so basically, what is this plot? Y-axis, mean absolute error. X-axis, what percentage is missing of your vol surface. The green models are the baselines, so stuff like Hessian with jumps, Hessian with the term structure, basically like classical approaches to filling in vol surfaces. And then the orangish color are the neural net approach. And what you can and so the first 2 lines for the orange are the non-residuals, and then the third one's the residual. And we can see that even in this scenario and the low missingness regime, it cuts the error again by half, right? And this is with hyperparameter tuning and everything to verify that like no model is somehow like, maybe it could easily have just picked a set of hyperparameters where one model does better than the other. But in this case, it's not that because we properly tuned it. And not in the slide, but I was helping somebody else at work. He was doing something with like fast pricing with a set of inputs. Also that one, when he switched it out to the residuals, it cut the error by a factor of 5 or something. And I think it's important that it's not necessarily, if even, a generalization thing. It seems it is purely an optimization problem, that doing this really gives you much better loss curves. And again, residual connections kind of are everywhere, right? Besides the fact that they're in transformers. So anything that's using a transformer has those residual connections. If you look at the literature for normalizing flows, some of the best ones there have some form of a residual connection. Diffusion models are basically also just residual models. So it's kind of just this consistent theme through all of ML that just residual blocks. It's good. Just what I could say there. One thing I think is important to note here is that also that it's important to make sure your baselines are good, right? Because in the original version of this, there was only Hessian compared against a VAE. And in that case, the VAE does better. But if you just make that baseline just slightly better and put jumps or a term structure, it like destroys the VAE. And again, this is kind of a good point to make that like if you don't actually use the right architecture, classical models will look better, right? Because it is hard, like, and I would argue this is part of the reason why there's sometimes this gap on how much machine learning is being used in practice, is because there is even these what seemingly small changes, let's call it, just an architectural change, can have massive differences in the final performance you get. And so when you're comparing against a baseline or a neural net, or even different types of neural nets like MLPs versus convolutions, I think it's important to make sure that like you check the literature and you use kind of what are the right ways to use those neural nets. Okay. So that's for the optimization. Let's actually try to put some domain expertise into our model, see what we can do about it. So if you remember in so this is kind of what the current model is, right? You got a time series, it goes into some sequence model, and eventually you'll get a beta at the end. So one thing we noticed in the results was that in the multivariate case, the EMA was the weighted linear regression was doing better. So since we know that that's actually doing quite well, can we just attach those components together? Can I just use my neural net in conjunction with the weighted linear regression? So what if instead of outputting beta, I output the half-life instead? Once I have the half-life, I can compute the alpha. Given the alpha, I can go to the weights. From the weights, I can get the beta. And all these operations are differentiable, so why not? You can use, like, this is, if you use any, like, if you use PyTorch or anything, as long as you're using differentiable functions, you can backprop through the whole thing and you can optimize it. And so what's the net result? Now what you're going to get is a model that I would argue you can kind of interpret a little bit more, right? I think if you just look at betas, it can sometimes be a little bit like, oh, but why this beta, why that? But I feel people tend to have a little bit more intuitions on like half-lives that, oh, I'd expect the half-life to drop during this period, maybe go up. And again, not always, but it gives a little bit more. And you can see that in the table, using this time-varying half-life improves. Time-varying, obviously, because it's a function of your inputs, right? So in essence, a way to start now making your half-lives dynamic. And again, and a learnable dynamic function. So I think one takeaway here is to kind of, if you start from your baselines, you can improve them by using neural nets. You don't have to throw those away, right? It doesn't have to be a game of 0 versus 100, like 0 neural net, 100. No. There's worlds in the middle, and you can kind of do some cool stuff there. So can we keep pushing it?
I have a question that's been in the chat room for a little while, but
Okay.
I think you dropped it out. So they mention that classical beta uses OLS.
Yes.
But it works when there's little autocorrelation in the X variable. And so the person is hinting that maybe you could use time series models like ARIMA and somewhat more sophisticated time series models. And so would you consider that just like a third baseline, and would you think about how do the same lessons apply to ARIMA, let's say?
Yeah, I mean, I think I would say you can think of it as another baseline that can be there. And if it does do better, my suspicion with most of these models that you can then also just incorporate that, like you can also make those parameters the output of a neural net if you think that those parameters are time varying. And usually in real life they are. I haven't run those experiments to know like how much better we get with those, but if there is, I don't think the lessons are caveated on the specific baselines as much as the lesson being how you can take what you know and what you suspect is actually a good way to model the problem in a classical sense. Because in finance, most problems have baselines. Most problems actually have reasonable models that are effective in real life. The only thing that's missing sometimes is that there's always some level of model misspecification. And one way to deal with model misspecification is just making certain parameters more time varying. And one way to do then and if you want to take that approach, you can then be, okay, instead of making it a function of time, I'll make it a function of other features and make that like a learnable function. Hopefully that makes some level of sense.
So in a way, the output of your neural network rather than the answer beta is the sort of parameter set of your baseline.
Yeah. And that's kind of basically all that happened here, right? Is that the baseline was a half-life, so I just outputted that. But we can go further. We don't have to just, we can, what if we, instead of outputting half-lives, what if we just output the weights instead? Is that better? Not a given, right? Because one could say that basically the baseline of the EMA is half-life, half-life to weights, weights to beta. And obviously, if we just use the neural net to eat away the whole process and jump straight to beta, it seems to be like, well, we'll see. But it seems to not work well in the multivariate case, right? So maybe there is a middle ground that works best. So in this case, where we output weights, you can do this. Just do the weighted linear regression, you have your beta. One thing we added, because there could be issues of this becoming singular, we just added 2 additional global parameters. And basically, you can kind of think of these 2 parameters as like priors on beta, right? Mu is like a good average guess for beta, and sigma is like the uncertainty on that. And why is that an okay interpretation to take? Is because the equation that we use for beta is basically just a regularized linear regression equation. And so that's kind of one upside of also using these baselines and marrying them with neural nets, is that you have often a lot of intuitions on your baselines, and those intuitions can help your design. So taking this approach, we applied it on all of them, and we do get significantly better performance. Specifically, we actually are able to outperform now the baselines for the multivariate case. And so the intuition, again, here being that basically it was able to, it doesn't have to learn the linear regression equation function from scratch now, right? It just has to learn how to be dynamic in a way. And again, we know that not being dynamic, just using one set of weights is pretty good. And then we're basically trying to boost that performance up by allowing the weights to be a function of the inputs. Okay, and so we have so the beauty of having these outputs being weights and stuff like that is that you can actually now look at them and see, do they behave in ways that make sense? So if you look at, for example, the step function model, basically on the left, we have example functions for beta, right? Yellow, beta never changes. Then the different colors are, it jumps down to 0 at different times. And then on the right, what we looked at is the predicted weights by our model. And then the reason it doesn't look noisy is that we basically averaged it across a lot of instantiations of the data with that specific beta function to see basically what types of average weights you get. And it kind of seems to make sense, right? That it does seem to basically up the weights when the jump happens, but it doesn't completely zero out the rest. Probably, again, has to do with the fact that it may not, there's going to be some uncertainty if the beta actually jumped or not and where it jumped. And so that's kind of where that lingering part comes from. But I think this is one cool thing to get to do when you have a model that outputs something that is, to a certain extent, intuitive. Similarly, we can look at the results for the market. So what we found was that in COVID, so the March 2020, again, we averaged across the different securities. We see that it kind of lowers the weight on the recent data. And you can kind of see on the right that it kind of seems to be correlated with the volatility, basically. That if it's more volatile, it tries to lower the weights a little bit. And I guess the intuition being there is that if you have more volatile data, basically it might get in the way of the statistical significance of your output. So it may be better to kind of rely when there's less volatility in the market. And further, I think this is kind of cool, is that in log scale, the weights are kind of linear in October, right? Give or take. You kind of have to kind of stare a little bit and dream a line, but that'll be a thing we push on a little bit more. Okay, so let's go further. What more can we do? So we've played with the outputs. We put some cool stuff in the architecture. Let's look at the architecture itself. Let's look inside of it. Let's see what else is going on. So one thing I mentioned is that when you're using attention, you have positional embeddings, right? You have something that encodes time inside the model itself. And the way you usually do it is you basically have like a mapping from like time step 1 will have this vector, and I'll add that in. This has time step 2 will have this vector, we add it in, etc. And so what is the usual way people do this? The standard way, sinusoidal embeddings. Basically, you have like a vector. The first element will be some sine curve with one frequency. The second one will be cosine with the same frequency. The third element of the vector will be a different frequency, et cetera, et cetera. And you kind of end up with like a pattern like this. The reason for this, right? Like, obviously people make these things for a reason. One thing is that by allowing this like sinusoidal behaviors to be in there, the hope is one, that it might be a little bit easier to generalize to sequence lengths it hasn't seen before, right? It's not encoding it as like 1, 2, 3, 4, 5. So 6 is all of a sudden unobserved, but it gets to see it as this like sinusoidal behavior. And also intuitively, it can help maybe with seasonality. If basically, you'll have to look at the way the attention function works, but by doing this, it makes it easier to try to attend on basically like 5, 10, 15 days ago, or multiples basically. But one thing we noticed is that when we grabbed a batch of data, looked at the weights and averaged it, we kind of got this shape. And kind of looking at it, it seems like there's a sinusoidal behavior in these weights, right? And if you remember with residual blocks, you can kind of think of it as that linear functions are really easy to learn. So kind of the behaviors you have in your inputs will pop out in the outputs. And so the question that I kind of had is that, is this just an artifact? Like, is this actually optimal, or is this just because we use the sinusoidal embeddings? So if we believe the intuition that something a little bit more monotonic is useful, what if we just swap them out with the linear embedding instead, right? This won't be useful when we want to, if you try to generalize to other sequence lengths, which is valid, but it might have fewer of these artifacts. And we actually see it does get rid of a lot of the sinusoidal embeddings. And actually, again, I should have log scaled this. It's really exponential. If you log scale this, it has basically like 2 linear shapes. And even though I said that basically you could think of it as like a linear function from inputs to outputs, I think you have to just train a lot of neural nets on different one-dimensional data. But if you train enough on different functions, you kind of pick up on what types of functions are easy to learn, right? So like a sine function is harder. Basically doing this like constant like second derivative changes is not, it takes time for a neural net to learn. But if you're doing something more monotonic or like parabolic, it learns it really quickly. Yeah. So does this actually help? We found yes. We're able to go from that 0.4% improvement to 0.5% improvement with this. Right. And so again, I think the important takeaway here is that sinusoidal embeddings is like the standard approach, but that doesn't necessarily mean that that's the right approach for your problem. If you know that that's a part of it, you can swap them out, see what happens. Might give you better performance. And then one last thing we did to try to improve performance is since we have these global parameters, mu and sigma, we were like, what if we initialize this at a value that we think is good, right? A decent value for beta is 1. People tend to use that if they're not even doing OLS. So what if we initialize it there? Could that help? And again, obviously, leading questions, the answer is yes. And it goes up further to 0.58. So I think a fair question here is why is this useful in this case? Like why wouldn't the model just learn this? Like if you're just gradient descenting it, the mu could just slowly move up to beta equals 1. So what happened? The intuition there is basically it's because they're global parameters. So when you're doing gradient descent with neural nets, you can kind of think of it as you want every parameter to just move a little bit. You don't want them to move too much. And in the case of a neural net, that's okay, because if all the parameters move a little, the overall function can change a lot. But in the case of global parameters, if each of those just move as slow as all the other parameters, they're kind of learning at different rates. That's kind of the intuition to have there. So possibly a solution that could have worked as well is just up the learning rate on those parameters, look at different optimization tricks. But I thought the easier one here is just to be like, look, I know beta equals 1 is not a bad guess. Let me just insert that in and see what happens. And again, the same idea here. You know something about the problem. You can actually then put that into your model itself. And that's basically all the NeuralBeta parts. And so I tried to kind of summarize this talk, let's call it like in a meta way of like what the general lessons, at least in my mind, are. So kind of like a recipe of how I approach these problems is like basically step 1, what do we do? Problem formulation, evaluation metrics, right? It sounds like the most obvious thing, but I've had enough conversations where people forget about what their evaluation metrics are, and they're just like, I want to predict that one thing. But it's like, okay, but how are you going to evaluate if that's the right thing? And think of your use case, right? You know, just because there's a thing that you could predict, the loss function may not just be mean squared error to that value. If you plan on using that prediction in a different way, it'd be better to try making a loss function based off the way you're going to use the predictions of your model. The example I kind of have is like forecast, basically like portfolio optimization type stuff. Most people will take the model and just try to forecast returns. But in the end, even if you forecast returns, you're going to then use that prediction. You're going to do long short portfolio, look at that. And so that's technically different than what you optimized your model for, right? So it's probably better to be like, if this is the approach I'm going to take, let's just train my model knowing that that's how I'm going to use this model.
Quick question. You express these in terms of percent improvements, right? And so you said something like, oh, this is 0.4%. Is this like a big deal, or like, for example,
That's a good question.
Economically significant if I hedge with an old-fashioned beta versus a fancy beta, and I guess is that difference worth it? You know.
So yeah, that's a good question. We I guess we didn't put that plot in the slides, but one thing we did was we actually did like break down the performance by time, because there are let's say regimes where there's not much of a difference. You could have just used the weighted linear regression and it's probably good enough. But it seems that the fact that the model is able to be very dynamic in certain situations really helps, let's say, in COVID. And that's where there's a huge boost in performance compared to like the baselines. And so that's another thing to always look at, right? It's like, again, breaking down your data into subsets and seeing what happens in those different subsets. But yeah, one thing, and also the point I was making, is that even if the percentage sounds small, at least the way I try to argue it always is that most people are going to implement a weighted linear regression over OLS, arguing that it's better, but the performance is 0.12% when you actually look at the numbers. So at least if you've convinced yourself that that's worth it, then I would say going from there to 0.58 is basically, like 5 times as much, right? So and those units sound huge. Yeah, so evaluation metrics. Second, baselines, right? Weighted linear regression, for example. Once you have that, re-implement the baseline in a differentiable manner, something like implemented in Torch. In the case of beta, this is kind of a trivial step, but this may not always be a trivial step. There may be algorithms you have implemented as a baseline that have if statements and parts like that. There may be ways to make it differentiable. One way to kind of make an if statement differentiable is using like a sigmoid function, which basically is like a 0-1 type function. So that's kind of one way to make it differentiable. But there can be different scenarios where it could be kind of a pain, but this is an important step when we get to the next step, where now you can start trying to insert parameters into your baseline itself, right? So importantly, we don't have a neural net yet. We're just putting parameters. So we could optimize the alpha of our EMA. We could optimize the weights, or the individual weights. For now, let's just focus on the EMA example, right? You can do that. And if you optimize it, you'll see that you can get a better performance versus if you hadn't. If that happens, then the next step is now you can try making those parameters the output of a neural net, right? What if I make it, how can I now make those parameters more time varying? Because nonetheless, most of the time, if you talk to most people, even if it's not time varying, actually, I think this is probably worth noting. It doesn't have to always be just time varying. Maybe it's just that you have a different parameter per stock, right? And sometimes instead of trying to optimize it, let's say non-parametrically per stock, it might be better to pool it together by having it be the output of a single neural net, which uses features of those stocks, right? Because one thing that's kind of a consistent theme in statistics is that let's not bucket our data. Can we find features that can explain the relation of all those buckets across each other, so that way you can improve the statistical significance of your model, right? And so that's another thing that's useful to do in that step. One thing I didn't mention here, but because for most people, this might not be the worst place to stop, right? You have a model that hopefully is better than your baseline. It's, it gets a little bit more dynamic, and it has outputs that you could do sanity checks against, right? Many a time, people have, again, intuitions on these parameters, and so then they can check, okay, I think that the relation between some input and output should be positive or negative. And you can try to analyze some of these patterns at least, just to be like, does it align with your intuition, and is your intuition right? One thing you could do next, which I didn't put here, is then you could start trying to eat away at your baseline with the neural net, right? So for example, in the earlier one where we outputted the EMA, the half-life, right? That's one way of following this whole thing, and it does better than just the EMA. But then you could say, okay, I'm going to eat away at one function, which goes from the half-life to the weights. If I do that, does my model do better? Am I okay with the interpretability of it and stuff like that? And of course, you could go further, eat away further, and just predict beta directly, which at least in our scenario, we found is actually not better to do it that way, right? But that's kind of like maybe a workflow to kind of think about when thinking about machine learning in finance in general. Cool. So to kind of just conclude, from the NeuralBeta perspective, many tasks basically in finance are about finding linear relationships between things, right? There's like stock beta, credit beta, delta, something called SSR, which is basically like the linear relation between the change in implied vol and the change in the log change in the underlying. So basically the idea is that we're basically replacing the estimator with the neural net, right? So, and I think also a theme you can keep in mind a lot, even with the recipe idea, that in essence, what you're doing is you're using a neural net as an estimator that can go from data to the parameters. You're not using the neural net as just the model of the world. And then, again, instead of you should try to, when you can, use a single model for all the securities you have across all of time. if there are things that you feel need more, like if you feel like, oh, it might do better with newer data than older data, either A, you should test it because there are a lot of times when that's not true. There is a value sometimes in just pooling more and more data together. And if it does actually do worse by using more data, I would recommend maybe looking at more features because I think in an ideal scenario, you should be able to pull together as much data as possible. Neural nets can handle these like slow and fast moving periods. And I think to me, I feel the biggest point is understanding the details of neural nets allows you to customize them using domain expertise. Thanks.
Anybody got some questions here?
So when you're using NeuralBeta, what is the difference between using a PCA or the autoencoder, which could be used like a dimensional reduction techniques?
So, sorry, where would the PCA part of this one be used? Is it to find the factors? Oh, okay. So so the question is about basically trying to use like say like how does it compare against using PCA for finding factors? It's a little bit different of a problem, right? If you kind of, I'm not going to go all the way back. If you remember, basically I kind of mentioned there's like 3 different approaches to factor modeling, right? One is like the Fama French style, and that's kind of like where this world lives in, right? Where you have a fixed set of factors which are observed, and then you're trying to estimate the beta based off that. In the case of the PCA, that's like the statistical factors. So that would be like the neural factors approach, where instead of the neural, and it's still a neural net spitting out betas, but those betas aren't in relation to some predefined factor returns. It's going to define some betas, then compute what the implied factor returns are given those betas, and then see does that fit the data well or not. And that's how you do that, where that would be more of the analogy of neural nets for PCA.
Any other questions from the local audience? We have one more online one, but do you have anything? Okay, so there's 2 online questions. The first one is about tuning neural network hyperparameters. How do you set the number of hidden layers and the number of neurons? Any approaches or strategies?
Okay. Oh, sorry, I was going to skim through the
There's
next part, just
another
in case.
question. Yeah, basically, are there yeah, the residue.
Yeah, the residuals.
The
Okay,
resi-
how to do those things. Okay, so like say like for tabular data, because that's kind of an often used use case. An advice I've given, which is it really seems kind of like out of nowhere, like why, but I found that 2 residual blocks, 64 or 128, and then 2 in the dropout, pretty good as like a good starting point. Like that, it served me well on a lot of problems. And then in terms of tuning hyperparameters, yeah, there's going to, I think tuning the hidden size, again, dropout, hidden size, learning grade is also pretty useful to tune. Yeah, I think those 3 are usually my go-to. I think people also say batch size. I've actually not tuned that enough, so I can't give too much of my own intuition on how important that one is. But definitely dropout, I would say, is like if you're tuning anything, tune the dropout. If you got more time, tune the hidden size. Number of blocks, I've yet to see doing more than 2 is good on real data. But for example, in the fast pricing problem, that function is so deterministic and there's no noise. That's one of the few problems where like adding more and more blocks helps. Basically, it's just about adding more parameters in that scenario. So that's kind of what I would recommend in terms of hyperparameter tuning. But again, default just 64, few blocks, your dropout will serve you well in your problems. In terms of implementing residuals, I can't speak for TensorFlow. I haven't used that in a long time. But for PyTorch, it's not too difficult. Basically, you would have to create, basically what I have is I've created my own like module class, which is just called resid block, which is just like that specific MLP block with the residuals. Once you have that module implemented, you can stack them really easily. Oh, actually, that reminds me of one set of hyperparameters. One thing that seems to be was really popular back 10, 12 years ago, but still makes an appearance once in a while, is like the triangular type structures of the hidden sizes, where like, I think usually they try going like really big and then they slowly like half their way down. I'll say there's no need to do that. Just use rectangles. Just keep the same hidden size through the whole thing. And that's kind of, I prefer like that. I think in general in life, you kind of want to see what you can do to remove hyperparameters. And I think the fact that block structures work really well, just stick with that. There are still scenarios where you want to reshape it, but that tends to come more in like images where you kind of have pooling layers. And so you have to increase the number of channels, but that's kind of like a very specific use case. But generally just block structures.
Okay, well, let's thank again our speaker for this tour of neural networks.